Yeah. Okay, guys. So if you manage to get to grips, or manage to go through the exercise, manage to get to grips with the work we did on the vector, where we left it with the last thing I taught you was finding the intersection of two planes, one of which we used the simultaneous equation method, which was, I think, fairly intuitively obvious how to do, but a bit fiddly, and then a little bit complicated, but I think more efficient to use, was using the cross product, understanding that when two planes intersected, the line of intersection would be perpendicular to the normal of both. So if you can take the normal of each plane and find the cross product, you've got a line that's perpendicular to both. And then you basically pick an arbitrary value of x or y or z to find a point on that line. Okay. Now I'm going to have a look at some applications of it, some of which may be hard. I think the first one is the most difficult. Now we've already seen this is yet another vector product or form an equation for a straight line. We've already seen R equals the most useful one, RA plus lambda D. We've already seen that form of the vector equation of the straight line. But there's another form of the straight line. Now, suppose I should say D really, shouldn't it? Between that should say D. So where I put D there, this is, suppose we have A is a point on the line, and D is the direction vector of the line, and R is the position vector at any point on the line, the X, Y, Z. You should be able to tell me something about the vector R minus A. Then R is the position vector of any point on the line. It's movable as X, Y, Z changes. The position vector of this point changes. It's always on the line. You should be able to tell me something about R minus A. Yes. The vector
or along
the line. It's a direction vector of the line. Let's find the difference between 2 points on the line. The resulting vector is parallel to the direction vector of the line. It is a direction vector. Does that make sense? Okay. Well, if you take the cross product, emphasize this, and I should have done it. If you take the dot product of two vectors, it means they are perpendicular, because if two vectors are perpendicular, cos theta is 0. If two vectors are parallel, then sine theta is 0. So if two vectors are parallel, their cross product is 0. Exactly, yeah. Exactly right. So from the definition we started with, you can also pick that, but you can't find a line, a direct perpendicular to two parallel vectors. In terms of the mathematical formalism, sine theta is 0. Okay. So R minus A cross D is 0. So R minus A parallel. And if you want to, make a note that the cross product of two parallel vectors is 0. Okay. And that actually is yet another vector equation of a line. So, for example, in this case, we would write R minus 5, 1, 2 cross. Okay, I need the direction vector for that. So I'm going to go minus 2, 1, minus 3. Is a vector equation of that line. Not, I find, a very useful one, except unless I'm doing an exam question that says find the equation of this line in that form. Okay, it's not one I would naturally use. Or because the cross product is distributive, you might also be expected to recognize that can be useful, because you can evaluate 5, 1, 2 cross minus 2, 1, 3. So you can write the equation in the form position vector, the point in the line, crossed with a constant position vector is equal to a constant. Okay. I don't think this form intuitively that meaningful. Correct me if I'm wrong. You might find a geometric interpretation of that, but I don't. I don't see it particularly. So I think I probably work out something to do with triangles. Yes, it's to do with. I mean, well, I'll try and find a video or something. I don't know. It's to do with if you move, you know how you move the height of the triangle along, you keep the area the same. It can be interpreted geometrically like that. I think. So vector product form an equation of a straight line. Find an equation of the plane. That's its main use. So I hope do that. Okay, we can start with that, Joe. I've got the 3 points in a plane, and I want the Cartesian equation. AB is good. Yeah, 2. Catch up with it. 2 minus 3, 1. You check on the right down, please. And we'll do AC. It doesn't matter which 2 we do. We'll do AC, which is minus 2, 1, minus 1. Yeah. Yeah, so, yeah. Yeah, so what I think what you were about to give me was R equals a point plus lambda that plus mu that. So that's a vector equation of the plane, but not a useful one. I asked for the Cartesian. I didn't say there. I'll say it here. I'll say I want the Cartesian equation. Yeah. So what would I do? So I find the cross product of these two. So what I'm trying to find, Joe, is there is a way of using dot product for this. We've done it, but it's the whole point is I'm trying to show you a better way. Yeah, I know that both of these vectors are in the plane, and I want to find the normal of the plane. We found this magical result that the normal of the plane gives you the coefficients of the Cartesian. All I need to do is do the cross product of these two, which is equal to, I do minus 3 times minus 1, which is 3, take away 1, which is 2. And the middle one, I do 2 times minus 1, which is minus 2. Minus 2, that's 0. I'm going to get negative 0, but 0. The bottom one, just check. Have I made a mistake? No. 2, take away 6, minus 4. This is the normal of the plane. These two are both. So we have, and I'm going to say that's equal to 2 lots of 1, 0, minus 2. So x plus 0, y minus 2z. And then I'm just going to go back to my point and use any one of those. So I'm going to get 3 minus 2 lots of 2 minus 1. I might try that with another point. 1, take away 2 lots of 1 is minus 1. And I might find one more point. 5 minus 2 lots of 3 minus 2. That works. It's interesting, of course, that it gives us a plane with no y coefficients. No y coefficient. Is there an interpretation of that? Parallel to the y-axis, perpendicular to the xz plane, to the xz plane, which would be the same. We always about that. I'm going to look at my room. There, so this is the xz plane, parallel. Yeah. Yeah. All right, this one. This is one of the ones that you found not easy when I first showed it. I now want to express something in words that I hope now you understand, and I think most of you did. I'm going to say the distance, the length projection of line joining in the direction of. Now, I'm now, after many years, in a position where I can visualize that confidently. I understand that it's clear what I understand. The job's done, I can move on. Or we can talk about it a bit more. I can try and show you the diagram to show you where that comes from. We go for option 2. Yeah, okay. So just to make sure we know that we understand the words, we know what projection means, though. Like the shadow or the component. Okay. The line joining 2 skew lines. So what I'm saying here is get the 2 skew lines and we just randomly join one point on one line to the other line. That's my line joining 2 skew lines. And I want to know what the component that is in the direction of the problem. And the reason I want that, I should have copied this there. Should have copied the across. No, it comes down to that diagram there that spends time around. Okay, here's my line joining the 2 common skew lines. So the 2 skew lines, and I can see from this diagram that the shortest distance between the 2 points is the same as the distance between these 2 planes. And I think there's nothing for it. I've got some videos I'm going to show you where to access as well. There's nothing for it. And to really keep looking at that diagram and you see where these planes come from. We want parallel planes. They're normal to both. The normal to the planes are normal to both those lines. And then all we need to do is find the components of that length in that direction. Okay. So I'm going to do it as so our distance. Okay, well, the line joining 2 skew lines, I think I can safely say is A minus B, where we'll say that's A, B, two random points of line. Okay, so that is now a vector joining 2 skew lines, and I want projection of that in the direction of the common normal. Now, remember, projection of A on B in general is equal to A dot B hat. Yes, I'm finished. It could be B minus A. A is the position vector of a point on one line. B is the position vector of a point on another line. I can choose any points on the lines that I like, but I might as well choose the 2 easiest ones. A minus B is a vector that joins the 2 lines. One of an infinite number of vectors that joins the 2 lines. And now, then the projection of A on B is A dot B hat. Again, I confidently know that, I fully understand that, so I'm happy to move on, but I can again go back to stuff. If you like. Okay. Okay, brilliant. And then you're already ahead. B is A dot B hat. So I want A on A minus B dot. Well, what's the direction of the common normal? It's oh gosh, B1. Sorry, I should say N. No, D1 and D2. So the common normal is D1 cross D2. So we're nearly there. That is the dot product of the line joining the 2 lines in the direction of the common normal. But what do I have to do? So that's like A dot. That's like a vector dot another vector, what I have to do to turn it A dot B hat. The magnitude, what you said is right, won't notice like that. Now that's a formula you can learn, which is how a lot of students do it. But I think I've got into the position where I can reasonably expect you can understand that. And if you have understood how those words turn into that formula, if you think that's easy, then you've really, really done very well. But it's not easy. If you can understand how to go from here, that's a huge, huge information. Very solid understanding of pretty much everything we've covered. Because it's all in there. It's got dot product, projection. I mean, if everyone understands that fully, I'd be both impressed with you and impressed with myself, slightly surprised. So please don't be afraid about asking. It normally takes longer. Yeah. So A minus B is so A and B. A and B are arbitrary points in the line. Are points in the line. The A minus B is a vector joining the lines. In other words, it's go back to my diagram. It's PA2. PA2. But it can also be the vector joining those. That vector, the projection of that vector in that direction is the same as the projection of this vector in that direction. Any 2 points projected in that direction have the same option. Yeah. Yeah. So I put that. A and B are points on the line. I'm not projecting a point on a point. Oh, sorry. This is in general. In general, I mean, okay. I'll change those. Yeah. Okay. I better. That's just a general. That's a general thing that sees. Have you understood what a projection is? The projection of x in the direction of y is x dot y. So I've used that formula to get this is my x and this is my y, and so that is my y hat. So y hat is a unit vector in the direction of y. Yes, the 2 direction vector. It will. Yes, but it won't. Right. So this is where I don't know if this is what you're asking. This is where sometimes it makes sense to use direction vectors in unit form. So if you had these were unit direction vectors, which I think is what you're sort of suggesting. If you had these 2 were unit direction vectors, then this would have magnitude 1. Right? So you would need to. Is that right? Is that even right? Because they're going to be say, no, that's not necessarily right. Now ignore what I said there. This is the unit direction. You have to do that's the magnitude of d1 done from d across d2. This has not got magnitude 1. So you have to divide by that. That is why that. Okay. Find the distance between parallel lines. Oh, I got this. When do we end? Good. This is between parallel lines. This is something where I think the textbook explains very badly, misses out a step. So I read the textbook and I thought, well, maybe it is obvious. It'd be obvious to you. It wasn't obvious to me. So I'm doing the same thing as the textbook. This is one where we've already shown a method for doing this. Okay. But I think this is better, but it is slightly different. We can't use the method above in that parallel. What we can do is this diagram here. We take two arbiters. Call that point A. And we're after this distance here. Maybe set for X, using as X for product of the same P. Yes.
Actually, sorry, I thought you were trying to show that parallel.
So these two lines are parallel.
Yeah, I thought you were trying to show that.
No, it shows that, yeah, that's obvious, right? Okay. That's minus 2 times that.
Yeah.
Okay. And what I'm trying to find is a peak. Okay, right. Now, can I see anything now? Well, I can see if I take that length, if I take that angle as theta, then I have sine of theta equals a over p. Oh. By the way, I mean, I'm going to show you this. I'm not going to. I would tackle this question exactly the same exam. I am going to derive a result, but do we know that if we call this line 1, that's the direction vector d1. That's the direction vector. Sine theta AP dB. We're trying to find AP. So AP equals AP over AB. Thank you. It's much better. Okay, now do we know psi theta at AB? We do know AB. Okay. If I take the cross product AB with EB, that cross product would give me, so these need to be vectors. That cross product, but let's forget about what the direction of vector means at the moment. The magnitude of that vector would be AB times EB sine theta. But if I divide this by the magnitude of EB, magnitude, I get that. Yeah. AB. Really don't worry about the end hat, but if you cross AB with EB, you get a vector with magnitude AB times EB from sine theta. This you can see is where it is important to be careful about whether I'm talking about vectors or not. AB is not a vector. AB is a length. AB here is a vector. Yeah. We'll see that. Okay. Well, let's apply it without don't really need to do every step. What's AB? Well, AB in this case is -2, -5, -1. That's a vector between two arbitrary points on the line. This is what's PB? Or at least a vector in the direction of PB. One minus 3. So we do that cross product, find the magnitude of it, and we divide it by 1 squared plus 3 squared. So we haven't needed to find the angle, we haven't needed. No, you could, of course, think about it. You probably have done that as a slightly advanced problem solved question back in 9 or 10. You've got all the basic trigonometry. But this is a nice, elegant way. And this is the one that I'm least confident about because actually it's not using any of the properties of the cross product really that we talked about. It's just using that trick. And finally, yes, it really is finally, the area of one parallelogram. Well, what's the area of triangle OAB? Or after half OA and 2B OA. Not product, that's just times. Can't be dot product, they're not vectors. That's half the magnitude of A cross B. And so for some of you, you're asking for geometric interpretation of A cross B. Well, we've got one now. A cross B. If I didn't have the half, can you see that any two vectors defines a parallelogram as well as a triangle? Two sides of a parallelogram, I could extend that and join that. So the area of a parallelogram is just the magnitude of the cross product of two sides. But if you know the coordinates of a triangle, now, I don't know if you ever remember doing this further down the school, but actually finding the area of a triangle based on just having coordinates is fairly big. You can do it even in first year by drawing a rectangle around it and cutting it into several triangles. You might remember doing that. It's basically now we've got a very, very nice one. We just find the vectors of the two sides and find the cross product. If you have the coordinates of 3 points, one of them is the origin, you just find the vector. Let's say that's point C. You would find CA and CB. And it doesn't matter which two sides you use. Okay. Yeah. It's twice the area of the triangle. Yes, you absolutely. That's exactly right, Albert. So now, if you like, think of the cross product as simply being a vector whose length is the area of the parallelogram made by two triangles, twice the area by two vectors, or twice the area of the triangle made by two vectors in a direction. Probably. What everyone wants is to have two vectors and to have a two-dimensional. Two vectors are in 2 dimensions and have a 2-dimensional interpretation. But you can't think about it because you can't find the cross product of 2-dimensional vector. Cross product, by its very nature, has to give you something in a 3rd dimension. Dot product, but it can be for any dimension.
So,
Lucy, I think Lucy.
You wouldn't be able to do that for 2 dimensions, would you?
No. I don't know if you define something that has similar properties to the vector cross product in 2 dimensions. I don't know. can.
Just think of a really,
Yeah, I suspect you can, and use it as an algebraic tool.
I was trying to think of a really elaborate way to do the area of a triangle, just given the points in 2 dimensions.
But we could do it 2 dimension. We just set that to 0.
That's what I also think about. Then
That will work. That will work. But the cross product is still something we get third direction.
but if you assume it has no component in the third direction,
That is now. If I was asked to find the area of a triangle in 2 dimensions, that's probably still how I do it now. And no one's my first stick off. You could, but that would be really using a sledgehammer to crack a nut. You would just write -2, 6, -4, -2, 1, -3, 2. If one vector is a multiple of another, apparently, right? So that would be quicker, I think, than doing the cross product. But you certainly could. If you find the cross product of this with this, you get 0. That would imply that. The dot product wouldn't. False negative one. If you really wanted to make it a very long way around, I suppose you could say the magnitude of the dot product is the same as the magnitude of that times the magnitude of that, which shows that false theta is 1, which shows the angle. But I mean, that would be to do if you had an hour left. But that's which obviously was. Yeah.
If you were to continue with that, like the shortest distance between the parallel lines.
Yeah.
Would you get like 1 over root 30 and then the vector? Or do you have to times the sine?
So it's got to be. It's got to be. No. You would get the whole point. This thing here is equal to that thing there.
Yeah.
So we're going to use this thing, not this thing, because we don't want to be finding sine theta. So
yeah.
This one will get a vector. Have you worked it out?
Yeah.
Okay. What do you get if you do the cross product of the
-7, 3, 11.
-7, 3, 11? I'll take your word for it. Over root 13. And then we need to work out the magnitude of the thing on the top, which is root 49 plus 9, 2, 1 over root 13.
And then that.
So I'm trusting your calculation of cross product. I haven't checked that. So if anyone thinks it's wrong, you can blame Ella. So root 179 over root 13. Okay, or you can blame me if it's the bit at the bottom that's wrong. Yeah. Okay. All right, that is it. That is the chapter finished. I'm going to give you at least a double and a homework, if not more, on working through a load of problems. Okay. So the no more theory. I'm not saying you're going to find the problems easy, but you've got all the tools to do now. Right. Let's see.